So we've learned about x to the first power, we've learned about x to the second power, and today we get to learn about x to the third power. So what does that graph look like? How does that behave? So let's start with a basic warm-up here where we're given a function. And so functions, we can plug in numbers. So we are plugging in 3 into this function and figuring out what does it output. So you can think of this number here to represent the x value that's being plugged in to this equation. So I'm going to have my x here is 3. So I'm taking 3 and raising it to the third power. So I'm plugging in 3 and I need to raise it to the third power. So that's going to give me, well, let's find out. 3 to the third power is like saying 3 times 3 times 3. Well, 3 times 3 is 9. 9 times 3 is 27. So it looks like 3 to the third power is 27. And same thing with this one here. I'm plugging in -3 for x, so this is going to be -3 to the third power. So I have to ask myself, what is -3 times -3 times -3? It might help to put some parentheses around here so we don't get confused with the negative signs being subtraction signs. But essentially what it's doing is if I multiply -3 with -3, I get +9. But I still need to multiply that by another -3, so that ends up giving me -27. So my answer here is -27. So anytime I'm raising something to the third power, I'm actually multiplying itself 3 times. So I want us to compare these two answers and ask ourselves, why is this one positive and this one negative? Think about it. So when I have something that is a positive number and I cube it, I'm always going to get a positive number because, well, there was never negative numbers to begin with. But unlike squares, whenever you have a negative number and you're cubing it, you're always going to end up with a negative number because, well, there's an odd number of negative numbers. So when you took something to the third power, notice there are 1, 2, 3 negatives. That means you're going to end up with a negative number because when you multiply these two, it ends up being positive, but then you got to multiply with this guy that's negative, so it turns back into a negative number. So what I want us to notice here is that when you take a positive number and raise it to the third power, it's always going to turn out positive. If you take a negative number, raise it to the third power, it's always going to come out negative. So from here, what I want us to do is, now that we're a little bit more comfortable with raising things to the third power, I want us to look at what does the graph look like for an equation like y equals x to the third power. So we've been studying y to the second power, which is a parabola, that U shape that we've talked about so much earlier on, but what exactly does x to the third power look like? And to do that, or to figure out what the picture looks like, we always start with a basic table. And I've picked out some x values to plug in, and we're going to find the y values. So just like before, we're taking our x value, plugging in for x, and then finding what our output is, the y value. So if I take -2 starting out and I raise it to the third power, or plug in -2 into the equation, -2 to the third power, if we just think about it for a moment, if you need a scrap sheet of paper, or just use a calculator, -2 times -2 times -2, well, -2 times -2 is +4, times another -2 is going to give me -8. So this is -8. All right, so the next one here, I'm going to be raising -1 to the third power. Now this one gets interesting because we know that if you take a 1 and you multiply it by 1, you're always going to get 1. But if you take -1 and multiply by -1, you get +1, and then you're multiplying it by another -1, so that ends up being -1. And then you could probably guess it, 0 to the third power is just going to be 0 times 0 times 0, which is just going to give me Let me just write this out. 0 times 0 times 0 is just 0. So 0 to the third power is just 0. That's pretty easy. For our next one here, we have 1 to the third power. So if I take a 1 and I multiply itself 3 times, that's just going to give us 1, right? 1 times 1 is 1. 1 times 1 is 1. So this to the third power is just 1. And then if I take 2 and raise it to the third power, instead of getting that, that negative 8, I'm going to get a positive 8, right? Because in this case, I don't have negatives here. If I do 2 times 2 times 2, I'm going to get 8. Because 2 times 2 is 4. 4 times 2 is 8. So I want you to notice that negatives come out negatives. Positives come out positives. So you can kind of see that, that reflection of negative signs. So let's go ahead and graph these because these are coordinate points. Essentially what I have here is a coordinate point at -2 and -8. So if I go to negative 2 here on the x-axis and go down to -8, that means I do need to extend this coordinate system to accommodate the large numbers here. So let me extend this to also +8. This would get me to, let's see, -2 down 8 is about down here. And then we have -1, -1, so that's going to be right here. And we have 0, 0, so that's the origin, so right about there. And then the next one's 1, 1, so +1 and up 1 would be right there. I'm going to plot that point. And then we have 2, 8, so 2, 8 is going to be up here. And plot. All right, looking good. So what I'm going to do is connect the dots. And let's take a look at the shape here once we connect the dots. You can see it's quite steep. Even from the left side, the negative side goes down pretty steep. And the right side also grows really up steep. So it increases steeply and it decreases steeply. And that's probably because you're raising things to the third power. So whenever you raise things to the third power, it grows very quickly because it's multiplying itself 3 times. And so in this case, what we notice here is this like shape that kind of looks like a lightning bulb is what I like to call it. It kind of looks like this side is moving up and this side's moving down. But one special piece that I want us to recognize is this middle piece. Now, we usually know the middle piece of a parabola to be called the vertex, right? We call that the vertex for parabolas, but in this case, we don't call this a vertex. We call this an inflection point. And I'll explain that maybe later on, but the middle part of a cubic function, this is what we call a cubic function because it's cubed or it's to the third power. So a cubic function has an inflection point as the middle point at the origin. This is also the y and x-intercept is also at 0, 0 because it's hitting the x-axis right here at 0, 0 and it's hitting the y-axis at 0, 0. And so because of this, this is what we call the parent function. It's the original function to the graph because it hasn't been shifted. It's sitting at the origin. So it hasn't been shifted left or right or up and down. Also, another thing that I love about cubic functions is that domain and range is going to be all real numbers. And let's investigate why this is the case. So remember that domain is associated to the x value, or what x value does this graph exist at. So in this case, if I look at this graph, notice it's stretching to the left. So if it's stretching to the left like that, it's going to be going towards negative infinity. And if it's stretching to the right, and notice it's stretching up, but it's stretching to the right, it's going to be going to positive infinity. And so notice there are no breaks here. It's going from left and right with arrows. So that's why the domain is all real numbers, because it stretches from left to right continuously. Now for the range, notice it's pointing down and up with an arrow. So it's heading towards negative infinity and positive infinity. So the range here is going to be also all real numbers for the y values. And so that's why I really love cubic functions, because they're easy to remember that the domain and range is always all real numbers. So let's also understand why the shape looks like this lightning bulb shape. And it's because, well, if you have negative numbers and you're plugging into cubic functions, you're going to get a negative number. And it's going to grow in that negative direction. And so that's why you see it pointing down. But if you have positive numbers and you're cubing it, it's going to grow positively upwards. And so that's why the shape looks like one's pointing down, one's pointing up. That's because you can plug in negative numbers and it's coming out negative, and you can plug in positive numbers and it's going to come out positive. So let's get into recognizing the different phase shifts for cubic function. And this is going to feel very deja vu or very familiar because we've done this before. So notice that this is kind of like vertex form for like parabolas. And so we might remember that if you have a parentheses with the x inside and you have like a minus or a plus a number, this is your horizontal shift. Minus means right, positive means left. If you have a positive on the outside, that means this is shifting up, negative means down. And then another thing we can talk about is the a, or the number in front of x. So a, you can, like I said a long time before, if you decide to use this as your slope, be very careful on how you use it. You can only use it 1 unit away, or in other words, your slope should always have a 1 for your denominator or your run. So if you have rise over run, a is going to be your rise and your run should always be 1. The reason why is the slope doesn't work after the run if the run were to increase. And this is mainly due to the function not being a linear function. This is not x to the first power, this is x to the third power. So it's going to grow quickly as the numbers increase. So you only want to use it when the run is 1. All right, let's talk about inflection points. So all of this helps us find, the shifts helps us find the inflection points. Likewise, before, it would help us find the vertex. So h and k, those values help you find the inflection point. So another thing I want to add in is if you have a cubic function, you will need to have 3 points typically if you want to graph. The inflection point is what you're going to need, the middle point, and then you're going to use the slope to find the 2 points on the sides. And 1 point, you're going to use the slope to find one side, and then you'll go in the opposite direction to find the 3rd point. And so this here is how we find cubic functions. You need 3 points to do it. Sometimes cubic functions can also be the other way. So instead of it pointing down first and then up, it can point up first and then go down. But you're still going to need 3 coordinate points before you can draw a cubic function. So let's get started with the graphing here. So in example 1, it wants us to graph the cubic function and describe some of the characteristics. So we will need to find the inflection point, Y-intercept, domain, and range. By the way, you can use a calculator here, and I'll show you in a moment how you can use the calculator to find cubes or take something to the 3rd power. So the first thing I want to start off with is graphing it, and that's using the phase shift. So the first thing I notice is there's a -2 on the inside. So if it's in the inside, this is going to be going right 2 units. And there's a +4 on the outside, so this is going to be going up 4 units. And this describes as our inflection point, or the middle of our cubic function. So if I go right 2, up 4, and plot, it's going to be right here on the graph, and that's going to be my inflection point. Actually, let me do that in pink so that we can see that a little clearer. So my inflection point is at 2, 4. And then the next thing I need to do is get 3 more points, because one of the things we mentioned earlier is that cubic functions need 3 points in order to graph. And that's the reason why is because we need to know like which way it's going up and which way it's going down. And so that's 2 more extra points after the inflection. So to do that, we need our slope. So our slope here is 1 because the number in front of this x is technically a 1. So we can say our slope is 1 over 1. Remember, the run always needs to be 1 here, and any number that is not written as a fraction, you can always put it over 1, so that's kind of nice. So I have to go up 1 over 1 and plot my point. And so I know that this side of the graph is going to be swinging upwards like this. And if I want to know where my third point is, I just go the opposite direction from the inflection point. So instead of going up 1 and over 1, I need to go down 1 and over to the left this time. And then I'll connect the dots, and this one's swinging downwards. And there we go. And so I have my graph here. And from this graph, the nice part is that the domain and range, like I said before, is always going to be all real numbers, because cubic functions always stretch to the left like this one's doing. It's stretching to the left with an arrow, and it's stretching right with an arrow. And so the domain is going to be all real numbers, and it's also stretching down with an arrow and up with an arrow, so the range is going to be all real numbers because the y's are going up and down. From here, we need to find the y-intercept. Now, y-intercepts are generally written as coordinates, where the x value is always 0 and the y value is where it crosses the y-axis. And you can see how I've drawn it. I haven't really drawn it enough where it would touch the y-axis. I could try to extend it, but if I'm trying to use my picture here, I don't know how accurate I'll get it to. So instead, what I'll do is what I usually do to find y-intercepts is to plug in 0 for x and solve for y. So to the side here, I'm going to plug in 0, use a different marker. So I'm going to plug in 0 for x and work this equation out until I have this part simplified. So inside the parentheses, remember order of operation, I got to do inside the parentheses first. So 0 minus 2 is negative 2. And I'm raising it to the third power. So that means I'm taking negative 2 and I'm multiplying itself 3 times. So that means like negative 2 times negative 2 times negative 2. So negative 2 times negative 2 is positive 4. And then if I were to multiply it by another negative 2, that just ends up being negative 8. 4 times negative 2 is negative 8. So that means that negative 2 to the third power is negative 8 plus 4 gives me negative 4. So that means that this here should have crossed the y-axis at negative 4. So if I were to extend this graph, I should make sure it hits it right there. But I don't really need to show that in the picture. For your picture, you do need to show at least like 3 coordinate points, like what I've done here, and just connect the dots. So that is it for this equation here. But I also want to show you guys how you would find negative 2 to the third power in the calculator. So in this next problem, I'll show you how to do it in the calculator. All right, so for this problem here, let's go ahead and find the phase shift first. So I notice there's a plus 4 on the inside, so this is going to be going left this time because it's a positive on the inside. And a negative 1 on the outside means I have to go down 1 unit. So if I go left 4, down 1, it would be right here for my inflection point. And so I'm going to record that inflection point at negative 4, negative 1. Now, from here, I need my slope because I need 2 more points to the sides so I can graph this. And so I can see this time my slope is negative 2 that's out in front. So if my slope is negative 2, I have to put it over 1 to make it a rise over run. And so this time I'm going to be going down 2 units. So down 2 units over 1 is going to place me about right here. And this is the first half of the cubic function. But I also have to make sure I graph the other side. So I'm going to go in the opposite direction. So this went down 2. I need to go up 2 and over to the left now. And plot. So that would be right about here. And I'll connect the dots. And now my cubic function is complete. One's pointing up, one's pointing down. And so I have that lightning bulb shape I'm going for. And remember, domain and range, just write that as all real numbers because it's pointing down and up. It's pointing left and right with an arrow. So Domain range is always going to be all real numbers. And now I need to find the Y-intercept. So the Y-intercept, that's where I have to plug in 0 for x and then find my y value. So if I take my equation here and plug in 0, I'm going to write it out to the side. Remember, order of operation means that I have to do the inside of the parentheses first. So 4 plus 0 is 4, but I have to cube it. So that's saying like 4 times 4 times 4 if I'm cubing. So I could do that in a calculator, or I'm going to show you how to do cubes in a calculator. If I switch my camera, see if I can switch that over. Give me 1 sec. There we go. So I'm in GeoGebra right now. If you guys don't know this website here, just type it into Google search. You'll find GeoGebra. And just type in GeoGebra Scientific Calculator, and this should pop up for you. You can also find this link on my homepage of Canvas. So what you got to do is click on the line here, and you'll type in the 4, or you could just use your arrow key and type in press 4. And then you're going to hit this button here, that square with a tiny little exponent box. If you hit that, it's going to cause this to have an exponent. So I'm going to type in, or just hit 3. And so it says 4 to the 3rd power is 64. So let's pause that there. And so that is going to be our value. So, all right, I just noticed a tiny mistake here. That should not be a 2 here. I don't know where I got this 2. It should have been a 1, so I must have accidentally carried down a 2. Don't know where it came from. Sorry, guys. So I'm going to fix that real quick. So there was a -1 here. I'm going to bring down that -1, and now we're ready to go. So as I mentioned before, this 4 to the 3rd power is actually 64. So let's go ahead and replace that entire thing with 64. And the next thing I would have to do is multiply, because the order of operations says multiplication would be first before subtraction. So if I multiply -2 with 64, I get -28, or -128. And I'll bring down the -1. That's to the side. If I subtract -1 from it, that just ends up being -129. And there we go. We have a very large number here. So it looks like my y-intercept is at 0, -129. And so this would have been really difficult to graph, because that's a very large number. I would have had to extend this very far down to show the y-intercept. So that's why it's nice to have, algebraic skills to be able to find it very quickly rather than to graph it. All right, let's move on to the next thing here. So in our next scenario, let me see if I can shrink this down and get rid of it at this point. I guess it won't go away. Oh well. So in our next problem here for part C, we have x minus 3 on the inside here. So the first thing I notice is there's not like anything outside the parentheses. So that tells me there's not an up and down shift. Instead, there's just a right shift of 3, since it's a -3. So we're going right 3 units. And so from the origin, if I go right 3, it would be right here. And I'm not shifting up or down because there's no numbers out here to represent that. So in that case, I'm thinking to myself, okay, so I guess my inflection point is at 3, 0. The y wasn't shifted because it's sitting on the x-axis. For the next part here, I do need 2 more points. So again, I'll need to find my slope here. So my slope is a 1 here, since there's just a 1 in front of my x. So I'm going to have 1 over 1. So I'm going to go up 1 over 1, plot. And I'm going to go the opposite direction. So down 1 over 1, plot. And I'm going to connect the dots. So this one's swinging up and this guy's swinging down. And so I have my graph here ready to go. Domain and range, always all real numbers, because the arrows are pointing left and right and pointing down and up. All right, the next part here I need to look for is the y-intercept. So the y-intercept is where I need to plug in 0 for x and find my y. So if I were to work this out, let's see, we have 0 minus negative or minus 3. 0 minus 3 is just negative 3. If I have negative 3 to the third power, I can use my calculator. Or if I do this by hand, negative 3 times negative 3 times negative 3. I just write it out 3 times. Negative 3 times negative 3 is positive 9. If I multiply that by a negative 3 again, this would give me negative 27. Actually, I think I've done this problem before in the bell work or the warm-up problem. Sounds a little bit familiar. So it looks like our y-intercept would be at negative 27, which would have been very far down the y-axis. So definitely didn't see that one coming. All right, so part D here gives us a function, or this equation here, that does not have parentheses. So if I don't have parentheses, I probably just don't have a horizontal shift, meaning I don't have any shifts that's going left or right. Instead, this is just a number that would have been outside my parentheses. So this is a minus 5. So I'm going to be going down 5 units. So I'm not going left or right because there's no parentheses here to show that. So I'm going to make it going down 5 units, which would be right here for my inflection point. So that would be like 0, negative 5. The x value here is at 0. The y value is at negative 5. Another thing I need to do is get the slope. So technically the number in front of my x is a 1. So 1 over 1 again. I'm going to go up 1, over 1 from the inflection point, and also going down 1 and over to the left in the opposite direction. And then I'm going to graph this up and down to connect the dots. Now here's the nice part. Notice that the inflection point is also a point that hits the y-axis. So I don't really need to calculate my y-intercept because I can technically see it on the graph. It's at 0, negative 5. It's the same spot as my inflection point. In fact, if I were to just plug in 0 for x anyways, I can see that my answer is going to end up being negative 5, right? Because the 0 just cancels out. And domain and range, all real numbers. So that's it for part D. Pretty easy with that one. All right, so on to our last two, which is part E here. So in part E, we have a problem where we are given a fraction in front. So things have just gotten pretty interesting. So this is where we can talk about why you have to be careful when you use the slope. So when we look at this here, let's first look at the shift. You have a minus 1 and a negative 2 on the outside. So minus 1 on the inside means you're going right 1 unit, and minus 2 on the outside means you're going down 2 units. So right 1 unit, down 2 would send you right here. So that would be my inflection point. And I'll write the coordinates out at 1, negative 2. Domain and range is all real numbers. And I need the slope. That's right. So now moving on to the slope, we have 1 over 2 in front of x. And one of the biggest mistakes people will make is say that it's 1 over 2, and they'll go up 1 and over 2 units. But you can't do that because you have basically your run here, or your denominator, is a 2, and that you can't do that when you have a cubic function. The bottom number should always be a 1. You have to be very careful when you use that slope. So this is not gonna work here. We're gonna have to backtrack. So let me go ahead and erase that. Sorry, I'm having a little bit of a glitch. There we go. So in order to force the denominator to be 1, we're gonna be very clever here. We're going to change the 1/2 into a decimal. And so 1/2 as a decimal is 0.5. And once you change that to a decimal, you can put that over 1. You can put any number over 1. And that forces it to be a 1 in the denominator. So that means you're going to go up a half, or 0.5. So the rise here is 0.5. So you're going to go up a half and over 1 unit. So this is allowing you to be very careful with how you use the slope. So notice if you were to do this trend here, the graph is going to look completely different. So if I were to draw this graph, notice that this is shooting up really high, right? Like it should be, because this is to the third power. Whereas if you went up one over here and then you graphed it, it would actually make it look less steep. And that's not correct, because this is to the third power. It's not a linear function. It's not going to move constantly like a linear function. So that's why you got to make sure that that fraction is changed to a decimal first, put it over 1 so that denominator is always a 1 before you graph. Now, since you went up 0.5, you're going to have to go down 0.5. Let me get my marker here. You can go down 0.5 and over to the left 1 unit. So I'm always going 1 unit from the inflection point. And that's something I want you guys to notice. I'm being very careful here. And then I'm going to graph it down, because this point went down. So this is going to go down. All right. And now I need to find the y-intercept. Now, it's probably, I'm not sure yet, but it's probably the y-intercept is at negative 2.5. But I want to be absolutely sure that this is the case, because I did estimate the slope. So I'm kind of curious whether it will turn out correct. So I'm going to double check. So if I plug in 0 for my x, I can find the y value like we've done before. So if I plug in 0, I can get an accurate reading on where the y-intercept should hit. So if I simplify the inside here, this would end up being negative 1. And I have to take negative 1 and raise it to the third power. So if I take negative 1, raise it to the third power, that's actually going to give me negative 1 back. We've probably looked at this problem before, but feel free to work this out on your own on a sheet of paper or use a calculator. And negative 1 times a half, anything times 1 is just itself. So this is negative 1/2 minus 2. So I've multiplied the negative 1 with 1/2, got a negative 1/2 minus 2. So if you want, you can change the negative 1/2 into a decimal if you're not comfortable with fractions, and just call it negative 0.5, and then subtract it from 2, which would also give you negative 2.5. So it looks like our number is correct with our graph that we made. And so this would be at negative 2.5 for the y-intercept. All right, last one here. This problem here is another fraction, so I definitely want to practice one more with you guys. So for this one here, you have a plus 2 on the inside, so we're going to be going left 2 units, and we're going to be going up 1 unit because of the positive 1. So if I were to go left 2 units, up 1, I would be right about here. And my inflection point would be negative 2, 1. So I have my inflection point. Domain and range is always all real numbers, just filling that in. And then my my slope here is negative 2 over 3. So now that we've been a little bit more careful here to recognize that we want to use the denominator to be a 1, let's change this negative 2/3 to a decimal. So if I were to put negative 2/3 in the calculator, or just take negative 2 and divide it by 3, fractions are basically division, you would get negative 0.66. So if I were to write it as a decimal, I could put it over 1. So I'm basically going down about 0.66. So if I go down 0.66, it's about 2/3 down and over 1 unit. About like right here, really close to the x-axis. And then I'm going to go the opposite direction. So I'm going to go up about 0.66 and then over to the left. And connect the dots. All right, so I have my graph, and now I want to find the y-intercept. So I'm going to plug in 0 for x and find y. So if I have negative 2/3 in front, plugging in 0 inside the parentheses, I definitely want to start with the parentheses. So I'll bring down the fraction. 0 plus 2 gives me 2. And then from here, I have to figure out what negative 2 to the third power is. Now, I've done this quite a few times now. 2 times 2 times 2, or 2 to the third power, is 8. This is actually a common exponent that we see So a lot of people will end up remembering 2 to the third power is always 8. So that's a very common number that we look at. All right, so this here you can change it to a decimal number, but I want to teach you guys how to be comfortable with fractions. So you can always put this 8 over 1 and just multiply the fractions out. So negative 2 times 8, because when you multiply fractions, you just multiply straight across. So negative 2 times 8 gives you negative 16 over 3. Now from here, you could change this 1 into a fraction if you put it over 1, and then try to get a common denominator by multiplying the top by 3. You could do that. And so you would have negative 16 over 3 plus 3 over 3. And so now you can add the top together. So negative 16 plus positive 3 is negative 13 over 3. So you can write your answer as negative 13 over 3, or some of you guys might have used your calculators and got negative 4.33 if you round. And so you can write this as a decimal, and usually it's what I recommend to write it as a decimal. So you'll get negative 4.33 if you plug this in the calculator. And decimals are easier for graphs just because they're easier to figure out what numbers they're between rather than a fraction. All right, that is it for this video.